Okay, this week we're going to be talking about logistic regression, and this is the final module in the course. What is logistic regression? All right, recall with multiple regression, the outcome variable was continuous. With logistic regression, the outcome is either binary or categorical, but in this class, we're going to focus on a binary outcome. All right, so an example there would be the student graduating from high school. Either yes, they did, or no, they did not. The student enrolling in post-secondary, either yes, they did, or no, they did not. This method is used to predict the probability of a binary yes or no outcome. All right, so again, we're predicting the probability. What we are not doing, we are not predicting the value of the dependent variable. Again, with that dependent variable being dichotomous or binary, only two options, we're predicting the probability of one of them happening compared to the other, as opposed to predicting the value like we did with multiple regression. All right, an example would be we wish to predict math exam performance, which we're going to call pass-fail, using three independent variables: time taking the exam, which is continuous, math efficacy, which is continuous, and English as a first language, which is binary yes or no. This requires logistic regression because of exam performance being categorical with two options. All right, let's go through some of our assumptions. Again, the dependent variable is dichotomous. So examples would be yes, no, married, unmarried, employed, unemployed, STEM or non-STEM major. And then one or more independent variables that are measured on either a continuous or categorical scale. All right, so let's go through a few of these. So continuous examples we've worked with, these are achievement scores, motivation, motor skills. And then we have nominal examples, gender, race, ethnicity. But let's talk for just a minute about ordinal examples. So ordinal means they are discrete responses. They are not continuous, but there's an order to them. For example, fitness level, where there's three options: low, medium, and high. Or Likert scale items, from like strongly disagree to strongly agree. Ordinal variables in logistic regression must be treated as either continuous or nominal. Is there a rule of thumb of when we can kind of get away with treating ordinal variables as continuous? Most of the research suggests that once we get to 5 or 6 categories with the ordinal variable, we could probably treat it as continuous. But if we only have 4 or 3, then we're going to have to treat it as nominal. All right, we've got independence of observations. All right, we've talked about this one before. This is when the categories of the dependent variable and any nominal independent variables are mutually exclusive, meaning you cannot both pass and fail the exam. All right, continuing with our assumptions. There's a sample size restriction with logistic regression. I would say that the base rule of thumb is that you have to have a minimum of 15 cases per independent variable, but some statisticians really recommend that you have up to 50 cases per independent variable. What do I mean by this? If you have 5 independent variables predicting your binary response, then at a minimum, you need 75 cases or participants in your data set. But some statisticians will recommend that you need really up to 250 as a minimum. All right, there is a linear relationship between the continuous independent variables and the logit transformation of the dependent variable. We'll talk a little bit more about the logit transformation in a minute. But this is something we're actually not going to be able to run in JASP. But if you were using SPSS or R, you would run a Box-Tidwell test, and statistical significance implies all continuous independent variables were found to be linearly related to the logit of the dependent variable. All right, there is no multicollinearity among your independent variables. So again, as a reminder, that means we want tolerance to be greater than 0.2 and the variance inflation factor to be less than 10. And then lastly, our common theme, no significant outliers. And in JASP for logistic regression, we're going to explore the residuals, and we either want the residuals, the standard residual to be less than 3, so we're going to call outliers those with a standard residual greater than 3 or Cook's distance greater than 1. And you'll see throughout the examples that I primarily am using Cook's distance greater than 1. And that, again, that's just a metric that's telling us if a residual has a distance that is greater than 1 in terms of Cook's distance, then that's saying, hey, you know, the model really had a problem with this prediction, and we've got to go back to the data point and either consider removing it or justify keeping it in our data set. All right, fitting a binomial logistic regression model. All right, it's going to look very similar to multiple regression. The big difference you're going to see is that a transformation is applied so that instead of predicting the category of the binomial logistic regression directly, the logit of the dependent variable is predicted instead. All right, but we continue, and again, this is for our population. We're using our sample regression to estimate these parameters for the population, and we have beta sub 0, which is our population intercept or constant, and beta sub 1, which would be the slope parameter for the first independent variable. And we have epsilon on the end, which represents the errors or residuals for the population. All right, but in practice, with your data, with your sample, you're estimating the binomial logistic regression model where you have B sub 0 as your sample intercept, B sub 1 as your sample slope parameter for the first independent variable, and so forth. And then we have E, which represents our sample residuals. And then notice we have this logit transformation on our categorical dependent variable. A logit is the natural log of the odds of an event occurring. Okay, it has little direct meaning. So the slopes that actually come out in the output, they don't have much meaning. They don't allow us much direct interpretation. And so what we do is we apply an anti-log or an exponential. We exponentiate the slopes to get to the odds ratios, all right? And this allows us to have a more interpretive meaning of these numbers. All right, there is an omnibus hypothesis test. All right, the null hypothesis tested is that there is no relationship between the outcome and the predictor variables. Significance implies at least one of the predictor variables has a significant relationship with the outcome. Again, this is very typical at this point in the class. You should be familiar with the omnibus test, not giving us specific details, but just saying that at least one of the independent variables is significantly predicting the outcome. All right, fit metrics for the model. So with logistic regression, we do get fit metrics in the output, and let's just go through the ones that we're going to take a look at in JASP. The first is the Akaki information criteria and the Bayesian information criteria. These are usually referred to as AIC and BIC, and these are measures of fit for the model. The best model has the lowest AIC and BIC values. And so in our output, you're going to see the AIC and BIC for the null model, which has no predictors in it. And then you're going to see the AIC and the BIC for our alternative model, which is the one with our independent variables. And we want that alternative model to have a lower AIC and BIC. All right, we get a pseudo R squared, and this is somewhat similar to the coefficient of determination in multiple regression. JASP calculates 4 values: the McFadden, the Nagelkirk, the Jur, and the Coxon-Snell. This pseudo R squared is pretty hard to interpret, but when you are comparing models, the largest R squared is considered to be the best. All right, walled tests are used to determine statistical significance for each independent variable. So after the omnibus test, we're going to get a p-value for each independent variable, and a walled test is used to calculate those p-values. And a walled test is similar to a chi-square test. All right, we also get something called a confusion matrix, all right, and this is a table showing actual versus predicted outcomes, and it's used to assess the accuracy of the model. All right, it leads to calculations for sensitivity and specificity, and you'll see when we report results, we want to be able to report the sensitivity and specificity of the model. Sensitivity is the percentage of cases that had the observed outcome correctly predicted by the model. So true positives. So if our outcome is yes, no, then it would be the percentage of cases that had yes correctly predicted by the model. Specificity is the opposite. It's the percentage of cases that did not have the observed outcome correctly predicted by the model. So these are true negatives. So this would be the correctly predicting a 0 in our example. All right, before we go into an example, let's talk just a little bit about odds ratios, because this is the output that we get in logistic regression that we use for interpretation and making meaning of the results. Odds ratios with groups quantify the strength of the relationship between two conditions. They indicate how likely an outcome is to occur in one context relative to another. Due to the odds ratio formula, the value of 1 becomes critical during interpretation because it indicates both conditions have equal odds. As the odds ratio moves away from 1 in either direction, the association between the condition and outcome becomes stronger. So, an odds ratio equal to 1, all right, this is telling you the numerator and denominator are equal. This equivalence occurs when the odds of the event occurring in one condition equals the odds of it happening in the other condition. There's no association between condition and event occurrence. If the odds ratio is greater than 1, the numerator is greater than the denominator. Hence, the event's odds are higher for the group condition in the numerator. And in public health research, in medical research, this is often a risk factor. So oftentimes your condition may be like risk of heart attack or risk of stroke. For us, it does in education and social sciences, it doesn't have to be a risk factor. It can be like graduating high school or enrolling in post-secondary. Odds ratio less than 1, the numerator is less than the denominator. Hence, the probability of the outcome occurring is lower for the group condition in the numerator. This, and again, in public health and medical research, this tends to be a protective factor. Oftentimes for us in social science and education, it's flipped. It's a little bit more of a risk factor. You'll see in some of the examples that I'm getting ready to go through that the denominator would be not graduating high school or not enrolling in post-secondary. All right, so let's do a JASP example. Using the Educational Longitudinal Study of 2002, we wish to explore if 9th grade math and reading achievement and gender predict post-secondary enrollment. And so the math and reading achievement and gender were all measured in base year, which was 2002. And then post-secondary enrollment occurred in, this was measured in the second wave, and I believe that was in 2009. I believe that was 2009. All right, so in JASP, if you're following along, you want to go to regression and select logistic regression. And we're going to put our post-secondary enrollment in the dependent variable. And we're going to put our continuous covariates, math and reading achievement, in under covariates. And since sex or gender here is a nominal variable, we put it in as a factor. And then under statistics, we want to check factor descriptives. We want to check odds ratios. We want to check confusion matrix. And we want to select both sensitivity and specificity. Okay, so in our first results, our model summary, we look at the AIC and BIC, and we notice that they are much smaller for the alternative model compared to the null model. So this is an indication that the alternative model is better than the null model. And again, remember, the null model has no predictors. All right, and in our omnibus test, with our chi-square value, we see a significant p-value of less than 0.001, which suggests a significant relationship between enrollment and at least one of the predictors. And then with our pseudo R-squared, we see that it ranges from 15.2% for McFadden to 17% for the juror. So we can say that explained variation in enrollment ranges from 15.2 to 17%. All right, so now we're going into our coefficients table. And as I mentioned, for each independent variable, we run a Wald test, which is a chi-square test, and we're getting a p-value on each independent variable. All right, and we notice right away that all predictors significantly predict post-secondary enrollment. And the most important values in the coefficients table are the odds ratios. For the continuous predictors, all right, so this would be our math and reading achievement, an odds ratio of greater than 1 suggests a positive relationship, while less than 1 implies a negative relationship. So here with reading, we see 1.039, and with math, we see 1.076. And so higher achievement scores are significantly related to an increased probability of post-secondary enrollment. All right, what about interpreting the odds ratio for sex? For the categorical predictor, again, an odds ratio of greater than 1 suggests a positive relationship, while less than 1 implies a negative relationship. For category 2, and notice in our table next to base year sex, it's telling us 2, and here 2 is female, compared to category 1, which is male. And so how would we interpret this? Females are 1.64 times more likely to enroll in post-secondary compared to males. All right, and then let's look a little bit at the performance diagnostics. All right, and we see the confusion matrix shows the model predicted 858 true negatives and 9,454 true positives. Sensitivity was 94%, all right, and 94% is the percent of cases that had enrollment correctly predicted. And with specificity, we've got 26.4%, and that's the percent of cases that had no enrollment correctly predicted. All right, and I want you guys to be able to do figures for logistic regression if you choose to do this for your project, so you can export some of these figures. So let's go back to the left-hand side in JASP, and let's select inferential plots, conditional estimate plots, and show data points. And what we're seeing here is going to be we're getting logic curve for each independent variable on the probability of enrolling in post-secondary. And so with reading achievement, we do see that reading the probability of enrolling post-secondary increases as reading achievement increases. All right, we see a little bit stronger of a relationship with math. All right, and so as ninth grade math achievement increases, the probability of enrolling in a post-secondary institution increases. And then lastly, we can look at our sex variable here, where again, 1 is male and 2 is female. And we can see that females are more likely to enroll in post-secondary institutions compared to males. Those horizontal lines you're seeing are the confidence intervals. And again, the fact that those confidence intervals do not overlap tells us that they're significantly different in the probability of post-secondary enrollment. All right, how do we report the results in APA format? Logistic regression was performed to ascertain the relationship of gender and ninth grade math and reading achievement on the likelihood of enrolling in a post-secondary institution. The logistic regression model was statistically significant, and we report the chi-square with the degrees of freedom, 13,287, and we report the value of the chi-square, 2,253.15, with the p-value of less than 0.001. The model explained 17%, and we let the reader know that that's Jur's pseudo r-squared, of the variance in post-secondary enrollment, and correctly classified 77.6 of cases. Sensitivity was 94%, and specificity was 26.4%. All 3 predictors were significant. Increasing ninth grade math and reading achievement were associated with an increased likelihood of enrolling, and females had 1.64 times higher odds of enrolling than males.